Okay, so in the previous video, I showed how to get the percent yield of water, which we found out to be 96.1%. All right, one thing I wanted to point out to you is that looking at the percent yields of the two products, you will notice that the numbers are not exactly the same. For CO2, we calculated 80.4. For water, we calculated 96.1. Don't get tripped out by this fact. This is something that oftentimes happens, experimentally speaking, and in practice. And the reason is simply that your techniques may actually be a lot better at isolating water, which is why you're getting such a greater percent yield for water than CO2. Uh, and this happens all the time. Different molecules have different ways of being isolated, so your technique may need some improvement for collecting CO2. That's all that means. I just wanted to point that out. I was running out of time on the previous video, but now that we've pointed that out, we can use the percent yield of CO2 to find out the amount of sodium chloride that we're going to be generating in this reaction. All right, so here we go. What we need to do is use the percent yield of CO2, which is 80.4, and we need to use the stoichiometry to find the theoretical yield. Together, those two parameters will allow us to calculate the actual yield of sodium chloride. So what that means is that we start with the limiting reactant, H2CO. We have the 10 mLs of H2CO. We multiply by the density of H2CO. And then we convert the mass of H2CO to moles using the molar mass. Okay, so this is once again the same type of calculation we did in the previous video. But now we're going to switch over to the moles of sodium chloride. And for every 1 mole of sodium chloride that we produce, we are using up 2 moles of H2CO, which is in essence the conversion factor shown here. All right, so the moles of H2CO cancel out. We now have moles of sodium chloride. All right, now using the molar mass of sodium chloride, we switch over from moles of sodium chloride to grams of sodium chloride, and the units cancel out aside from grams. All right, now carrying over the calculation, we have 10 multiplied by 0.815, you press enter. Then divide by 30.03, press enter. Divide by 2, press enter. Multiply by 58.4, press enter, and you should get 7.92 grams of sodium chloride for this calculation. All right, now this is the theoretical yield of sodium chloride that you expect to get. We are going to assume for this problem, because that's what we're told, that the percent yield of sodium chloride is the same as CO2. So we're going to set up the equation right here. We have the percent yield. We have the theoretical yield. We just found that using stoichiometry. We just need to rearrange this formula to find for the actual yield. And that means that we will multiply both sides by the theoretical yield and we will divide both sides by 100%, yielding the following setup. All right, so we've literally just rearranged this equation to yield this one. And now we're going to solve for the actual yield. So we input the percentage of CO2, which we're assuming to be the same as sodium chloride. The theoretical yield we calculate to be 7.92, and we divide this by 100. And what this will tell us is the mass of sodium chloride that we expect to get experimentally. Not the theoretical yield, but the experimental actual yield. All right, now this is a little addendum that can take place in this type of problems. All right, now the last thing we'll do is determine the amount of excess reagent left over in the reaction. All right, and we already know that H2CO is the limiting reactant, so by default, sodium perchlorate will have to be the excess reagent. And like any good old stoichiometry problem, we will have to start with the limiting reactant. Even though our interest is now on the excess reagent, we still start with the limiting reactant. So the 10 mLs of H2CO, we start with that. We use the density to convert to mass. We use the molar mass of H2CO to convert to mole. So this, yet again, same calculations. It's the same calculation that we've done the entire time through. And the reason why is because we're using the limiting reactant to go to moles of limiting reactant, and from there we can go every which way we want. We can go to the other reactant, we can go to any other products, we can go any way we want. And we've basically done that in this video and the previous one. Right now, we're interested in finding out the information pertaining to the excess reagent. So now we look at the ratios. We have 2 moles of H2CO for every 1 mole of sodium perchlorate. So you start with 1 mole of H2CO, you divide by the 2 moles of H2CO and multiply by the 1 mole of sodium perchlorate based on the balancing coefficients of the balanced equation. The moles of H2CO go away. You now have moles of sodium perchlorate. And lastly, since we are given the grams of sodium perchlorate, we want to switch this over to grams. So we use the molar mass of sodium perchlorate, 122.44 grams divided by 1 mole. And we have the moles on the bottom because that way the moles of sodium perchlorate will cancel out in the equation. All right, so now we carry over the calculation. We multiply 10 by 0.815, press enter, divide by 30.03, press enter, divide by 2, press enter, and multiply by 122.4 grams, press enter, and you should find out that the mass of sodium perchlorate is 16.6 grams. All right, now, from the stoichiometry, what this mass represents is the mass of sodium perchlorate that got used up, the amount that is no longer there, the amount that actually reacted away during the course of the reaction. So what is left to be done to find out how much excess amount is left over is to subtract this amount from the initial amount of sodium perchlorate that we used, right? So excess amount equals actual amount minus amount used up. So that means that 20.4 minus 16.6 will give us the amount left over, the amount of sodium perchlorate that's actually still present in the reaction flask. In this case, 20.4 minus 16.6 means that we have 3.8 grams of sodium perchlorate left over. This will be the answer regarding the amount of excess reagent left over. The amount in green, in the green box, is the amount that got used up. All right, so with that, we are basically done with stoichiometry. One thing that I will remind you of is that you, in the course of a reaction, are going to end up with amounts of products. And you will also end up with some amount of leftover excess reagent. So excess reagent products, as many as them as you have, are going to be present in the same flask prior to purification. So it's not out of the question for me to ask you not only for the amounts, but potentially the concentrations of the excess reagent left over behind in the flask and the concentration of the products that you're forming. So keep in mind your concentrations, what they stand for, and the conversion stoichiometry that I'm showing right here. All of this will kind of coincide and merge together to give you a much more comprehensive way of looking at chemical reactions.